This is part 2 of derivatives and the shapes of curves. So for this next question, we are looking at using the first and second derivative tests, and we're going to put them together. In part 1, we looked at the first derivative test, and we looked at the second derivative test, and we looked at them separately. Now we're going to put them together, and we're going to find the intervals of increase or decrease. That's with our first derivative test. We're going to find the local max and min, again with our first derivative test. We're going to find the intervals of concavity and the inflection points. That's with our second derivative test. And we're going to put all of this together to draw a very informal sketch of what the graph would look like. So let's see if we can figure this out. So the first thing that we need for our first derivative test is our first derivative. So here we are given our equation f of x equals 2x to the third minus 3x squared minus 12x. So let's go ahead and take our derivative of that. So pause the recording, take your derivative, see if you can do that without me, and then rejoin and check your derivative. So if we want to take our derivative, we'll have f prime of x is equal to 6x squared minus 6x minus 12. That should be what you get for your derivative. I see a common 6, so I'm going to go ahead and factor that out, which will leave me with x squared minus x minus 2. We want to know where this equals 0, so I'm going to go ahead and put the equals 0. I can divide both sides by 6, so I'll be left with 0 equals x squared minus x minus 2. I can factor that. If we do x minus 2 and x plus 1, it'll factor quite nicely. Then we can say x minus 2 equals 0 and x plus 1 equals 0, which means we'll be left with x equaling 2 and x equaling negative 1. Now from the first video, we only had one critical number. This time we have two critical numbers. If we have two critical numbers, that means we're going to be splitting our interval from negative infinity through infinity into 3 pieces because there will be 2 division intervals. So the first one will be at negative 1 and the second division will be at 2. So that means that we have negative infinity to negative 1 as our first interval. Then we have negative 1 to 2 as our second interval. And then we have 2 through infinity as our third interval. So we found two critical numbers, negative 1 and 2, and we used those to split our interval from negative infinity to infinity in 2 different places, making 3 different pieces. So now we do the same thing that we did before. We need to figure out the sign of our first derivative in each of these intervals. So if we're trying to figure out the sign of our first derivative in each interval, we need to pick a number that's within each interval. So I'm going to pick negative 2. I'll switch colors so it doesn't blend in. So between negative infinity and negative 1, negative 2 is in that interval. So I need the sign of the derivative, so I'm putting this back into the derivative. Now you can put it back into any form of the derivative. I like to use my original because if I made a mistake with my factoring or something like that, I won't catch it. If I use the original, then I have hopefully avoided any mistakes that I may have made in my derivative calculation further down. Even though it was just translating it and doing algebra, it's possible there's a mistake there. So I like to go back to my original, which means I'm going to go back to f prime of x becoming, f prime of negative 2 equaling 6 times negative 2 squared minus 6 times negative 2 minus 12, putting my negative 2 back into the original. It doesn't matter what the value is, what it matters is the sign of it. So negative 2 squared is going to be 4. 6 times positive 4, it's going to give us a positive number. It's going to give us positive 24. The 24 doesn't really so much matter. What matters is the positive. Negative 6 times negative 2, again, that's a positive, positive 12, minus 12. Well, these will cancel off. It'll be positive 24, but what I care about is that it is positive. Positive is the piece that we needed. So now let's do the same thing. Let's pick something between negative 1 and 2. 0 is in that interval. I like 0. Let's use 0. So that means f prime of 0 is what we're checking next. So go ahead and put 0 in where you see your x's. and we can see this will become negative 12. Anything times 0 is 0, so 6 times 0 squared is going to be 0. Negative 6 times 0 is going to be 0, so we're left with negative 12, so that means this is negative. Again, we didn't care about the 12. That part wasn't important. What was important is the negative. So now let's do one more. We need to pick something between 2 and infinity, so I'm going to pick 3. So that means we need to check f prime of 3, which will look like 6 times 3 squared minus 6 times 3 minus 12. So if we do 3 squared is 9, 6 times 9 is 54, minus 18 minus 12. It looks like it is still going to be positive. You can calculate it through, you can get the exact answer, but it's going to be positive, and that's the piece we care about. So we need the positive here. Okay, now let's look at our signs. Let's see if we can figure out the signs. If it is increasing, it's going up. If it is decreasing, it's negative, it's going down. If it's positive, it's increasing, that means it's going up. So it looks like here we're going up and then down. So that means negative 1 is going to become our max. Here we're going down and then up. So that means that 2 is going to become our min. Now we need to figure out the values at negative 1 and 2 so that we can have our coordinates here. So let's figure those out. Now negative 1 and 2, those are going into our original function because we're finding the value of the x. That's another reason that I say in the derivative only the sign matters, not what the actual number is, because I don't want it to get confused with when we're solving for the other half of the coordinate and needing the actual number. The actual number we're solving for is going to go back into the original equation. So I have x is negative 1. And I'm trying to figure out what the coordinate is going to be. So that means I need f of negative 1. So that'll look like 2 times negative 1 to the third minus 3 times negative 1 squared minus 12 times negative 1. And if we solve all that down, again, we're looking for the coordinate here. So we're solving it down. We need the actual number. Well, negative 1 to the third is going to be negative 1 times 2 is negative 2. Negative 1 squared is positive 1, so positive 1 times negative 3 gives us negative 3. Then we have negative 12 times positive 1, or excuse me, negative 12 times negative 1 is positive 12. So it looks like we get 7. So 1, 7 becomes the coordinate for our maximum. Now we need to do the same thing again over here for our minimum. Let me erase this min right here. So we have some space, so we can write it in. So we need f of 2. So that's going to look like 2 times 2 to the third minus 3 times 2 squared minus 12 running out of space times 2. There we go. So if we substitute everything in, well, what's that going to look like? 2 to the third is 8. 2 times 8 is 16. 2 squared is 4. 4 times 3 is 12. And then we have 12 times 2 is 24. So it looks like when we solve this all down, we're going to get negative 20. So 2, negative 20 is going to be our coordinate for our min. All right, we got a lot of information here. Let's write this down. So our maximum, it looks like we found that is negative 1, 7. Our minimum, it looks like we found that is going to be 2, negative 20. We got those pieces. Now it's asking us to find the inflection point and the intervals of concavity. So that means that we need our second derivative. So if our inflection point and our intervals of concavity tell us second derivative. So let's see if we can find a second derivative here. So I'm going to go back to our original first derivative. We've got all of this for our first derivative and our different intervals. So we don't get confused, I'll make some space. So it looks like we need that part. All right, So let's pick up from here and let's find our second derivative. So again, give it a pause, find our second derivative, and come back to check when you've got it. So our second derivative should be 12x minus 6. So if we look for where that equals 0, we can solve it down. So 12x minus 6, so 6 is equaling to 12x. Divide both sides by the 12, and it looks like we get 1/2 is equal to x. So that means that our split of our intervals is going to be at 1/2. So we're going to have negative infinity to 1/2 is our first interval, and then 1/2 to infinity as our second interval. So we need the sign of the second derivative. So if we need the sign of the second derivative, that means we need to pick some points and plug them in to figure out our sign. So in our interval from negative infinity to 1/2, 0 is in there, so let's pick 0. So if we look at our second derivative, and we're looking for x being 0, it's going to look like 12 times 0 minus 6, which means it's going to turn out to be negative. It'll be negative 6, but again, that's not the part we're concerned with. We're concerned that it's going to be a negative. And if it's a negative, then that means that it is concave down. There we go. Now we can do the same thing, and we can figure out what it's going to be from 1/2 through infinity. So 1/2 through infinity, we have a 1 in that interval, so let's try that one. So that'll give us 12 times 1 minus 6, which is going to be positive. So 12 times 1 is 12, subtract 6 is 6. We don't care so much about the 6, we care that it's positive. So in this interval, it will be positive, which means that it's going to be concaved up, which means that our inflection point is going to be at 1/2, and we need to figure out the other half of the coordinate. Now we're finding a coordinate again, and if we're finding a coordinate, then that means that we are using the original equation. So we're finding a coordinate, so that's going to look like f of 1/2 is equal to 2 times 1/2 to the third minus 3 times 1/2 squared minus 12 times 1/2. If you want to put that into your calculator, you can. If you want to multiply it all out, you can, but you should get negative 13 over 2. So what that means is our inflection point is going to be negative 13 over 2 for the y-coordinate. So now we've found a lot of information. We have our max, we have our min, we have our inflection point, we have our increase, we have our decrease, we've got our concavity, we've got a lot going on here. So let's see if we can draw a sketch for what our graph is going to look like. So I'll just make some space right here so we can see our sketch. We don't have a lot of information, but we have enough that we can draw a pretty basic, and I do mean basic, sketch. So let's put on what we know. So we know our max is at -1, +7. So I'm just going to put it right here. This is going to be 7. This is going to be -1. And then we know that our min is at 2, -20. So 2 can be here. Maybe I should make this a little bit longer. -20 can be about here. So 2, -20. There we go. We know that we have an inflection point at 1/2 and -3/2. So -13/2, excuse me. -13/2 is -6/2, so a little bit less than halfway. Let's put it right here. We're going to call this -6, and we'll make it -6/2. 1/2 is pretty small, so right about here. That's going to be our inflection point. We know that at the inflection point, concavity changes. We know this is a min, so we know it's going like this. We know this is a max, so we know it's going like this. We know right here, concavity changes, so we're going to do the best we can to keep it curving, and then keep it curving. There we go. A very rough sketch, but a sketch of what our equation would look like. Let's try part B. So in part B, we're looking for all the same information. We're looking for the intervals of increase and decrease. We're looking for the max, the min. We're looking for the intervals of concavity. And we're going to draw a very basic sketch to see if we can put it all together. So here we go. First, we need a derivative. So as before, take the derivative and put it all together. So in natural log, the derivative of the natural log is 1 over whatever you have the natural log of. So in this case, x to the 4th plus 27, and then times the derivative of whatever you have the natural log of. So in this case, the derivative of x to the 4th plus 27, and that is going to give us just 4x to the 3rd. There we go. There's our first derivative. And you're probably already thinking, oh no, we're going to have a crazy quotient rule for the second derivative. And you're right, we are, but we'll tackle that when we get there. So let's see what we can do here. First, something to notice. Look at this denominator. Look right here, x to the 4th plus 27. That is going to always be positive. We will never get a negative in that denominator because anything to the 4th power is going to be positive, and then you're adding a positive value to it. So x to the 4th is already positive, and you're adding a positive to it. It's never going to give us a negative value. So we know already that there will be no zeros from the denominator. So the only zeros of this function are going to come from the numerator. We can't have a 0 because we're adding that 27, and we can't have a negative because we have to the 4th, and then we're adding a value. So the only potential we have for a 0 is to consider where our numerator might be 0. And our numerator is only going to be 0 when x is 0. Because that's the only way we're able to get 0 from x to the 3rd times 4. You could divide both sides by 4, you'll get x to the 3rd equals 0, and the cube root of 0 is still 0. So that means 0 is what's going to divide our interval. So our interval, we have negative infinity to 0, and then 0 to infinity. The bad news is that means we can't use 0 as one of our check values, but that's okay, we'll make do. So now we need to find the sign of our first derivative. So if we're looking for the sign of our first derivative, then that means we need to pick a number that is in each interval and plug it in. So if we pick a number between negative infinity and 0, let's pick negative 1, and let's see what happens. So if x is negative 1, and we look at our first derivative, so that means that we're looking at f prime of negative 1. We're going to get 4 times negative 1 to the 3rd over negative 1 to the 4th plus 27. We know this denominator is always going to be positive. That's never going to change. In this case, it's going to be positive 28, but the 28 doesn't matter. What matters is it's positive. In the numerator, we have negative 1 to the 3rd. That's going to stay negative. So negative 1 to the 3rd times 4, that's going to give us a negative number. It's going to give us negative 4, but again, we don't care about that part. We just care that it's negative. So we have a negative divided by a positive, and a negative divided by a positive is always going to be negative. So in our interval from negative infinity to 0, the sign is always going to be negative. Let's do the same thing again, and let's check between 0 and infinity. Well, let's use 1. So that will give us 4 times 1 to the 3rd all over 1 to the 4th plus 27. Same logic as before, the denominator will always be positive. So let's look at the numerator. In this case, the numerator, well, that is giving us 4 times 1, essentially 1 to the 3rd is 1, and that's going to be positive as well. So this interval, the sign of the derivative, is going to be positive. So if we have negative, that means that it is decreasing. If we have positive, that means that it is increasing. So that means that our 0 right here is going to be a min. And it's going to be a min because it is going down and curving and going up. So now we need to find the actual value of the y-coordinate. So our min, we know it's going to be 0 comma something. So let's see if we can figure that out. So putting it back into our original equation, that will give us f of x equals, let me scoot that over some before I run off the page. the natural log of 0 to the 4 plus 27. Well, 0 to the 4 is 0, so this will be just the natural log of 27. And I'm just going to leave it like that instead of switching it to a decimal. Now we need to see if we can figure out what the second derivative is telling us. So that means we need to find our second derivative, and we need to check all of the points of our second derivative. So let's clear up some space over here. There we go. So we need a second derivative. All right, well, we can do it. Let's practice our quotient rule. So our quotient rule says the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator all over the denominator squared. There we go. Now the good news is the denominator is always going to be positive. We already figured that out before. The bad news is we have to mess with this numerator to try to see how we can factor it, and the way it is now is not going to factor for us nicely. So let's multiply it out and see what we can deal with. So let's just look at the numerator. So we're going to say this is going to go to just looking at the numerator. If I distribute this out right here, it's going to give us, so we're just going to switch this over and we're just going to look at the numerator. So it's going to give us 12 x to the 6, and then 12 times 27 is 324 x squared. And then let's do the same thing over here. Nothing to distribute, we just got to multiply these together. So 4 times 4 gives us 16. It's a negative, the subtraction between, so we're going to keep that subtraction. And 3 and 3 adding our exponents gives us x to the 6th. Okay, well, that's not too terrible. I see x to the 6 right here, and I see x to the 6 right here. So let's keep going with this and see if we can clean it up a little bit. So I have 12x to the 6 minus 16x to the 6. So that's going to give me negative 4x to the 6th plus 324x squared. Well, let's see, is 324 divisible by 4? Turns out it is, so let's pull out, so keep this going. So let's pull out our negative 4, let's pull out x to the 2nd, and that's going to leave us with x to the 4th minus, I pulled out the negative 4 so that I would switch it over to a minus in hopes that I'd be able to factor it further. Let's see if it worked. So 81 times 4 is 324, so negative 81 times our negative 4 will give us 324, so we're good, and then our x squared. And it worked. This will factor a little bit farther, so negative 4x squared, and then we'll have, this is a difference of squares, so x squared minus 9, and x squared plus 9. X squared plus 9 I can't do anything with, but x squared minus 9 I can, and x squared plus 9 is going to always be positive as well. So we still have 4x squared. X squared minus 9 is still a difference of squares. And I still have x squared plus 9. Okay, so let's see what we can figure out here. The x squared plus 9 is not going to give me a 0. I cannot put any values for x in there where I'm going to result in a 0. It's not going to work. So we are only going to get a potential 0 from negative 4x squared, from x minus 3, and from, whoops, that was supposed to say x plus 3. And x plus 3. So our potentials for a 0 are going to be 0, 3, and negative 3. Those are our only potentials for where we can get a 0. So that means that we're going to split our interval into 4 sections because we have 3 values that are going to split it. So we'll split right here. So this one will be negative 3. This one will be 0, and this one will be 3. Those are the only places that we're able to get a 0 out of this function. We don't need to consider the x squared plus 9 because it will never get us a 0. We don't need to consider the denominator because it will never get us a 0. If they would have given us a 0, we would have considered them, but they won't, so we don't need to consider them. So we're looking at places where we could get a potential 0. So let's keep going. Let's see what we can figure out from here. Well, let's do the same thing that we were doing before. So we have our 3 potential inflection points right here. We have our -3, we have our 0, we have our 3. So now we need to see what is happening at these different points relative to our concavity. So we need our second derivative. So our second derivative is all the way back over here. And we need to test each of these points. So start with one and work your way through. So if we're going to test each of these points, we need to test each one separately, and we need to test it into our second derivative. So let's start with our first interval. If our first breaking point is going to be -3, then that will be, there we go, -∞ to -3. Our second will be -3 to 0. We'll have 0 to 3, and then 3 to infinity. So go ahead and pause our video, take a couple seconds, maybe a minute or two, and see if you can figure out the sign of the second derivative in each of those intervals. Once you figured it out, come back and double check. All right, so I got negative, positive, positive, negative. So check your signs, put them back into your second derivative equation. Don't worry about the number, just worry about the sign. So if it is negative for our second derivative in our first interval, what does that mean? Fill in your concavity line. So negative means concave down, positive is concave up again, and concave down. So which ones of these are going to give us inflection points? Well, our inflection points are where the change in concavity occurs. So it looks like we'll have an inflection point at -3, and it looks like we're going to have an inflection point at 3. Now we need to put these back into our original equation. So remember, our original equation was the ln of x to the 4th plus 27. So f of x equals. So if we use -3, we're going to get -3, and it's going to be raised to the 4th power, which is going to give us 81. And then 81 is going to be added to 27, so it'll look like the natural log of 108. And then the same thing with 3. It'll also be the natural log of 108, because now it'll be 3 to the 4th, which is also 81, plus 27, so 108. Okay, we didn't have a max, that's okay. So now we can draw our sketch of a graph. Let's go with what we have. So the natural log of 108, you probably don't know that one off the top of your head. So it's okay to type it in and see an approximate value. I wouldn't convert it to a decimal. If you want to, go ahead. I would just leave it so that it's exact. But it works out to be about 4.68. So if we're looking at our inflection points, we have 2 of them. We have our 4.68 and our 4.68. And if we look at 0, we want to know that would give us 0 to the 4th plus 27. So we want to know what the natural log of just 27 would be, and that's going to correlate to about 3.29, but I wanted to write the natural log of 27 there. There we go. So that gives us enough information. So about 3 and a little bit. So I'll put 3 here, I'll put 4 here. So 3 and a little bit, about 3.29. That's going to be 0, 0. That gives us a point. It can help us out. So then we had our -3 and our ln of 108, and that's about, so -3 can be right here. That's about 4.68, so we'll put it right about here. And then we had our minimum at 0, so we figured out our value for our minimum, that ln of 27. See, we had it right here. So our minimum, we don't need to include it as an inflection point. We already had it over there. So we have that one. We have 1, 2, 3. That'll be about here. Okay, let's see what we can figure out. So we know that it is decreasing. So decreasing until you get to 0. We know that it is concave down from -infinity to -3. So this is going to be this way. We don't really know a whole lot about what's happening. It's decreasing, so we're okay on that part. We know that we're decreasing right here from -infinity. I didn't draw that very well. It looks like it's increasing. Let me try again to make it a little bit clearer. Whoops, didn't mean to erase that dot. Here we go. We know that we are changing our concavity to concave up, so it's going to look like this. Decrease concave down, but still decreasing. See how it's sort of curved down? And we're going to change it to curving up. And then it is still curving up. See right here, concave up goes to concave up, see? So it is still concave up. Right here. And then we're switching to concave down, but we still need to be increasing. So it's going to look about like that. So it's a rough sketch, but we can get a good idea of what our curve will look like. So that's going to end recording 2. Go ahead and switch over to recording 3 to pick it up with question 5.